Well, greetings, mathletes, and welcome back. Today we're going to be finishing up our talk about solids of revolution. We're going to change the perspective a little bit. The process is pretty much the same, but this time we're going to be focusing on rotating around the y-axis. I think I made mention of it towards the end of the last lecture, but we're going to take a look at that right now. So let's go ahead and get started here with our first example. We already have the basics of the concepts about this. Before, well, is that going to draw? There it goes. Before, our discs were encircling the x-axis, right? We would cut a disc out of here, right? And that's how we would, excuse me, that's how we would work our area out is discs that are oriented straight up and down. This time, though, we're going to be changing where our discs are, and they're going to be circling the y-axis instead this time. And the real difference that you have to be watching out for on this, there really isn't a lot of procedural difference. What is different is that you have to rewrite your function so that instead of y being a function of x, x is a function of y. And so that's what we're going to be working on today. So let's go ahead and clear that off and take a look at our first example. So all of these examples will be y-axis. Oop, that's not what I wanted. There we go. They'll all be y-axis rotation, right? So we're revolving around the y-axis. We're spinning like a top. So let's look at our first example. So let's say we want something that is bounded by y equals x squared, y equals 0, and x equals 2. So if we're looking at this, actually I'm looking at this and I'm wondering if this y equals 0 is actually even necessary, because this doesn't have any values below 0 anyhow. So anyways, let's go ahead and take a look at what this looks like and what it might look like once we rotate it around the y-axis. Okay, so first of all, we have y equals x squared, which is a parabola, right? Looks something like that. Let's see if I can draw the other side without... Well, we'll use our imagination for the other side. Notice these two sides are identical. So once you notice that, you really only have to deal with half of it, right? I really only need to deal with the part of the parabola that's to the right of the y-axis. So the positive side of it, the positive x values. Or you could choose to just use the negative x values also, but the positive ones are going to be a little bit nicer. Now let's look at our other boundary. So y equals 0 is the y-axis, and or the x-axis, excuse me, I said that backwards. And you can see I'm not sure that was necessary, but x equals 2 though, right? If x equals 2, one of the things you do need to know is what the y value is when x equals 2 also, because if x equals 2 is a boundary, that means whatever that is, I know that this shape, the part I'm revolving, is going to be all contained inside this box here, from where x equals 2 cuts that thing off. And so because this is x squared, if x equals 2, then y equals 4. Okay, and that ends up being important. So this point, because it's a boundary, we need to know both the x and the y coordinates. Now, what we're going to be doing from here is revolving this thing around the x-axis, or around the y-axis. Boy, I keep saying that backwards. Right? So that means we're going to end up with a solid that looks something like this. Right? So what we really need to do is be able to carve out one of these discs and then find the appropriate stuff about that disc. Okay, so let's look at it. Yeah, in fact, let me get rid of this because in my mind, this keeps looking like one of the axes. So I'm going to do this, and then I think we'll just switch the color so it's clear that this is a boundary. In my mind, I was revolving it around that point, and that's actually a whole different process. Okay. So let's look at one of these disks now. So this is my y-axis, and I'm revolving around that. So that means my disk is going to look like this. And I have a radius of this disk right here. Now, so we have to find the radius of this disk, because what we're looking for, we need to find the surface area of the disk and then multiply that by its thickness to find the volume of that disk. And then we're going to add up all the disks together from y equals 0 all the way up to the top of this, which is at y equals 4. So that tells us our limits of integration. So let's look at this disk here. So this disk, I know the surface area is going to be pi r squared, right? That's my area. And so I need this radius as a function, and it's going to be a function of y, and it's going to come out of this y equals x squared. If y equals x squared, then x is equal to plus or minus the square root of y. Now that's not a function, right? Because I have two y values for the, I have two input values here. So that's, two output values for this one x value. But remember, we're only talking about half of this parabola being rotated. So I can just choose to use the positive values. So what I'm going to do is just, for the moment, I'm just going to forget about the negative part, because it's just going to be, it's on the other side anyways. It's included with the disk. Okay, so this is one disk, which would be pi times, well, it looks like it's the square root of y squared, right? And so that's one disk, and now I have to multiply by the thickness of that disk, which is dy, because it's a change in y this time. Okay, now that's one disk. We need to add all of them up from 0 to 4. So that's actually my integral. It's now the integral of pi, and I can simplify this a little bit. If I square the square root of y, I end up with just y dy, and I need to integrate that from 0 to 4. Now, I do want to actually say something. This is a technical detail, and it's only true. The only reason that I wrote y here is because I'm only dealing with positive values. The integrals from 0 to 4, and that means there's no negative numbers in here. Okay, that would be a different story if there were negative numbers in this integrand, because technically, if I take it really should be a square root. Actually, no, it's not even that. Actually, it goes imaginary, right? If I plug in negative values for y here, I'm taking square roots of negatives. I was actually thinking of something else. I'll show you that in a second. So that means you'd have complex numbers in here, and that does cause some problems. The other thing to remember is that if you do it in reverse, right, if I square the number and then take its square root, that's the same thing as the absolute value of y. So those are just a couple of asides there that might pop up later. Not this semester, though, because we're almost out of lectures. Okay, so in any case, we can go ahead and compute this integral, right? Because pi times y is the surface area of one disk times the thickness of one disk, which is my dy, and then I want to add all of them up, so that's my integral from 0 to 4. And so this is now pi times the integral from 0 to 4 of y dy, which means that it is pi times y squared over 2 evaluated from 0 to 4. Right? And that actually works out pretty nicely. Because if I use the fundamental theorem of calculus, that means that this is now pi times 4 squared over 2 minus 0 squared over 2. And that's 16 divided by 2 is 8, so we end up with 8 pi here. Right, and so the volume of that particular, and just because it's interesting. That particular shape, when you rotate a parabola like that, is called a paraboloid. And so we just found the volume of a paraboloid. Okay, so that's our first example. And you notice it's a lot like our first example we did with the x values. There's a square root involved. You square the square root, so you don't have to worry about it. But it is ultimately just an application of the area formula for a circle. It really is. Okay, so let's go ahead and take a look at another one here. All right, so let's look at the next one here. And again, this is y-axis rotation. Oh, here we go again. There. So this is and the functions we are looking at that bound this region are y equals x cubed, and we're going to take the region from x goes from 0 to 3. Okay, and that's the region we're going to rotate around the y-axis. Okay, so let's take a look at what the picture looks like. And we know the cubic function does something like this. X is going from 0 to 3, which means that we are bound here and here. We'll just call this 3 because I feel like calling that 3. So the part between the y-axis and excuse me, and the cubic function here is this part, right? It's this shape right here that we're looking at, and we want to rotate this about the y-axis. So again, we're going to have to get a hold of a disk. So that means it's going to rotate all the way over to here. We're going to have this kind of a situation going on. And we are also going to have a disk in here. Oh. Well, I thought we were going to have a disk in here. We'll try. Right? And so we need the radius of that disk, which is the distance between the y-axis. I'll write it down here. It's the distance between the y-axis and the function, right? Which means if we rewrite this function as a function of y, it will give us our y distance. It will give us our x distances instead of our y distances, right? And this is a distance between 0 and 3 at this case, right? But down here, it's just the distance between 0 and the function, whatever the function happens to be. So we need to figure that out in terms of that. So in terms of function of y. So if y is equal to x cubed, then x is equal to y to the 1/3 power. Okay, so that's our function. That's our radius. That's our r. And so if we can, hopefully you're getting to the point where you can start to just set up the integral immediately. So we're going to need our limits of integration. And I know this starts at 0, so I'm going to put that one in because I just know that one already. Then I have that pi, and I'm always pulling the pi through the integral anyways. So I'll go ahead and put it on the outside to start with. And then I need my r squared, which would be y to the 1/3 squared dy. The dy is the thickness of your disk. Now if I go ahead and multiply this in, this is y to the 2/3 dy. And we still need the upper limit of integration here. So what we need to do, right, because we're going to be integrating from y equals 0 up to whatever this function value is, right? And if I plug 3 in here, I can figure out what y is, right? If I make x 3, y is 27, right? So y is equal to 3 cubed, which is 27. That's my upper limit. So I'm doing the integral from 0 to 27 of y to the 2/3. That's really what I'm looking at. Well, that's just a power function, so that means we can evaluate it. That's going to be 3/5 times y to the 5/3 evaluated from 0 to 27. Okay, so the 0 is going to be the easy part. So we'll handle the 27 first, right? So we have pi times, oh, it's not an integral anymore. That's what I meant to do. 3/5 times, excuse me, it would be 27 to the 5/3. Oops. Minus 3/5 times 0 to the 5/3. So 0 to the 5/3 is 0. I don't have to worry about that. Okay, so this part right here goes to 0. So I just need to worry about 27 to the 5/3. So if I look at this, let's just do a little scratch work on the side here. Get this out of the way for the moment. We already saw where that came from. Right, if I take 27 to the 5/3, oh, that's interesting. Okay, so what that is the cube root of 27 raised to the 5th power. So far, so good. Cube root of 27 is 3. See, I did that right? Yeah. Cube root of 27 is 3. So that means this is 3 to the 5th, which is 243. Do I have that right? It looks wrong for some reason. No, that's right. Okay. Sorry, I'm just double checking myself as I go. So that means that 27 to the 5/3 is equal to 243. And so that means this is pi times 3/5 times 243. And that part's 0, so I don't have to worry about it anymore. 3 times 243 is 729 over 5. And so it's 729 pi over 5. And so that's the volume when it's a cubic and you go out to 3. Right, but you notice it's the same process each time. Figure out what the function is, draw a disk, figure out what the radius of the disk is, and then you just put it into the formula once you figure out what the radius of the disk is. All right, so let's look at our last example here. And I figure we'll get some trig involved because I like to get triggy with it. So this one I'm actually going to give you as a function of y to start with. Where's the brushes? There we go. So we're going to say, again, this is still y-axis rotation. X is equal to the square root of 2 sine 2y. And we're going to have y go from 0 to pi over 2. Okay, so we need to get a sense of what this thing looks like. Now, even if you don't know what the function looks like, and this is one of those things that's kind of interesting, you can still plug in values here. 0 and pi over 2 are nice values to plug into sine, so they're probably things that you'll be able to take square roots of. But nonetheless, if we look at this thing, it's actually it bulges out here. It kind of flattens out around the square root of 2, and then it kind of lays back down. This is a horrible drawing. It looks very similar. If you continue this, it keeps bumping around. But if y is going from 0 to pi over 2, that's actually those are good boundaries. And so we're going to be rotating this thing around the y-axis, right? So that means we need to carve out one of these fancy schmancy discs, right? So we're looking at that. And so again, I need the radius of the disk. And so what I end up with is the integral, and it gives us the limits of integration here from 0 to pi over 2 of, well, I'm going to put my pi here, and I know whatever I'm putting here is going to be squared. The square root of 2 sine 2y squared dy. Okay, well, the square root and the square cancel out. We're only integrating over positive values. So it's 0 to pi over 2 of 2 sine 2y dy. Well, the integral of sine 2y is negative cosine 2y over 2. So this now becomes this. Put the pi on the outside again. This would be 2 times, I don't want to make that look like subtraction, negative cosine 2y over 2, right? So those will cancel. Evaluated from 0 to pi over 2. Right, so I can actually just look at this. This is pi times, actually I can put the negative, can I put the negative on the outside? I'll put it on the inside, it's better. Of negative cosine 2y evaluated from 0 to pi over 2. Right, so we're going to start out by evaluating at pi over 2. So this is pi times, let's see, the cosine of pi over 2 would be cosine pi, which is negative 1. And so this is the negative of negative 1. And it would be minus, and let's see, now we're going to put in cosine of 0, which is 1. But this negative makes it negative 1 again. Right, so this actually ends up being pi times 1 plus 1, which is 2 pi. Right, so we just found out that that area is 2 pi. Notice once you get it set up, the calculus isn't any more difficult than anything else we've done. It's the same stuff that we've done all this time. The difficulty is being able to see this, right, and knowing what this looks like. Even if you don't know what it looks like, oftentimes you can just draw an arbitrary function if you happen to know some of the endpoints. Like we can calculate what this is. We can calculate this for both 0 and pi over 2, and we can do the same thing with its integral. And so you can figure out these endpoints are going to be nice endpoints, right? Just by plugging in a couple of things, finding out that x is 0 when you plug in 0 or pi over 2 to that particular function. So you know that's actually where it's traversing, so to speak. All right. So that's, let's see, is that all of them? Yes, that is all of the examples. So we got to see one of the more straightforward examples, right, which was our square root example, which was just the y equals x squared. Then we got to play with cube roots and fractional exponents, and now we've looked at a little bit of trig. So all of these things are basically tools to find volumes. That's essentially what it's for. And that's pretty much how you end up using it. There are some minor little tweaks that go on with this, like it gets used in slightly different ways. And we will look at some of the more nuanced things in the next lecture. So until next time, keep your pencils and your wits sharp.